Screen 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 mic busy. Hello, am I audible now? No? Hello. ये audible नहीं है. Excuse me. ठीक है, ऑन ही नहीं हो रहा है. Okay. Thank you. Hello. Good afternoon. So today's lecture will be lecture 8, which is on calculus of subgradients. I think we have had sufficient motivation so far for the whole concept of you know, first order properties of convex functions. So this is what we have done so far. Motivated first order convexity. In fact, even finally gave you the proofs of equivalent definitions of first order convexity in the last class. And then I left you with a homework problem on second order properties of convexity, right? Any, I hope anyone, if you have had doubt, you'll bring it up front, right? So this was our first order definition, basically in terms of a supporting hyperplane to the epigraph of the function. And this is being visualized in the space of the domain plus 1. Just domain is Rn plus 1, which is the function value, right? Whereas the notion of sublevel set and quasi-convexity was all with respect to the Rn itself, right? The domain itself. So that's how it helps to visualize this in 3 dimensions. And I said there's a second order property also. Second order property basically is saying that if I take any 2 directions, so first order property said I take this gradient direction and add a -1 component. Gradient, if you remember, our visualization was that there's a gradient lying in Rn and there's a -1 component. This gave you the supporting hyperplane. I mean, it actually gave you the perpendicular to the supporting hyperplane, right? That's how it lies. Okay, in this case, it's gradient will be a gradient is in this direction. hope this is clear. Right? In second order, what are we saying? Well, if you take any direction, a random direction v, any random vector v, again in this space. So let's say my vector v is here. If I take the quadratic form v transpose into the Hessian of the function times v, this is going to be greater than or equal to 0 for all v. Basically, is wanting to say that the Hessian is positive semi-definite. And what basically this means is that the curvature is going to be positive in any direction. So this v, whether it's this direction or some other direction, right? In this plane, I hope you can visualize. Yeah, slice the curve in any direction, the curvature is going to be always positive. So I hope the 3D plot there makes more sense. Here I've shown this arbitrary curve and I mean arbitrary vector. And as I keep moving the vector, I'll always have positive curvature. Okay, so we saw this property and I had left you with a homework problem, specifically to show that the log sum x function, right, log sum x function, if you take the Hessian of log sum x, pre-multiply by v transpose, post-multiply by v, you'll get the same. You can prove the same, right? Anyone? Did you try attempting this? Some honest no's are. Can there be an honest yes as well? Anyone? Okay. What would you do if I were to ask you, right? So first of all, the Hessian you'll need to compute by doing composition of derivatives, right? Chain rule. So you'll look at the double derivative of exp, sum exp. So sum exp will basically be a sum of the Hessians of the exps. So when you do that, of course, the sum of the double derivative of exp itself is exp. But specifically, what will happen is when you take the derivative with respect to the variable xi itself, along the diagonal you'll have the exp xi's. But any of the derivatives across xi xj, so in this case w1 wj, okay, they will all vanish, right? So this structure is pretty much important, right? If you take a log of that, what will happen? Log of this sum, huh? So what will you do? You have to do element of sum, right? It's not element of. It's a log of the sum of the exps. But the Hessian will remain a Hessian. So it's basically going to be all the mixed partial derivatives for which you derive the elements in the matrix. And so will the zeros remain zeros? Right. So I'll do that in the next slide. Okay. So just for your information, I have posted. Somebody was asking, are there notes for convex optimization? Yes, they're already posted. On page 67 of this convex optimization notes, you'll find a table of some convex optimization problems. What I've done specifically is written there what the gradient or Hessian looks like. I think it's important for you to derive. So what is it? It is a diagonal of z's. Z is basically this ex1, ex2, etc. That's what I showed you, right? So if you want, right, so you'll have the diagonal of ex's, which is nothing but ex1, exn, with off diagonal elements all 0. That is the diag z. And then outside you'll have, so because of the derivative with respect to the log, if you apply the chain rule, you'll end up having a summation. Okay? This is a sum, sorry, log of the sum because of the log of the sum, you'll have summation. I'll just write that form here. 1 transpose Z, which expands as summation over EXI. Then there is another term. So this entire term minus, so there is going to be off diagonal elements, okay? There are non-zero off diagonal elements, and that is because of this ZZ transpose. So what is ZZ transpose? It's basically E x1 x1 E x1 x2 x2. That's the diagonal elements. Off diagonal elements will be E x1 x2. In general, E xi xj. Okay, that's how this matrix ZZ transpose will look like. I won't bother with this remaining part, which is just by virtue of log. Log gives you 1 upon Z transpose, 1 upon the sum of the x, right? That's coming here. Is that clear? Okay, so the question is then, what happens if I put a, because going back this is my Hessian. I put a V transpose here and a V here. What do you think will happen? Pre-multiplying by V transpose, post-multiplying by V. What is this? 1 transpose Z.
Positive semi-definite.
Positive semi-definite, positive semi-definite. Minus, this is minus here. Be a little careful. Right? So what would happen? Is it as simple, or there's a little bit more work to be done? So I must tell you, one of the, at least during my BTech days here at IT Bombay, one of my favorite inequalities was the Cauchy-Schwarz inequality. Okay, so any inequality, I would try and see if I can map it to that, especially when it comes to such non-trivial Hessian positive semi-definiteness. What do you think you'll do? How do you get to Cauchy-Schwarz inequality, if at all? In fact, we'll today see a generalization of Cauchy-Schwarz as well, called the Holder's inequality. So how will you apply Cauchy-Schwarz? 1 transpose Z, do I need to bother about it? It's just a sum of EXPs, right? Diag Z. Can I just take V inside here? Right, I'll just take V inside here. I'll take V inside here. That's possibly my recipe to get to Cauchy-Schwarz, right? Okay, so this is what I do here. So I have this diag Z, which is in pink, and the ZZ transpose in green here on the slide. So I have here expanded. Okay, so what happens if I take the V, when I take the V and push it into the multiplication with the highlighted matrices in pink, V transpose diag Z. What does it look like? I don't want to spend too much time, so I've written it down for you. It will basically be a summation over I of Vi square Zi, because I'm not pushing only V transpose V, right? So V transpose Z transpose V transpose diag Z transpose V. I'm sorry, diag Z into V. So this pink part is very simple. Vi square Zi. The green part requires this, that V transpose Z transpose V is V transpose Z whole square. And that will give you, summation over I Vi Zi whole square. What do you do next? Now you have got to the Cauchy-Schwarz inequality, right? I have done the simple substitution. See, it's all about substitution. That's another thing you should do. You get a complex expression, try and simplify. E raised to xi is Zi. Likewise, I have now substituted Vi into square root Zi as xi. and yi square root zi. Then I can just apply Cauchy-Schwarz inequality to the parts in gray and blue, right? Xi and yi. Is this clear? Okay, so that's it. I think that's the proof. So the rest is basically here, right? Y transpose y into x transpose x minus x transpose y the whole square is greater than or equal to 0. Actually, the moment you say di z minus zz transpose, this is again a very standard recipe. Somewhere or the other, Cauchy-Schwarz will be helpful. Okay. Any questions on this? So this was for log sum x. You can do this for quadratic as well. This is very simple. X transpose ax plus b transpose x plus c. That should be fairly straightforward, right? Quadratic or linear, which is x transpose y, x square divided by y. So this basically will have divided by y cube, unfortunately, in the denominator. And this matrix of y square minus yx is symmetric matrix y square x square. How do you prove that this is positive semi-definite? Sorry? Symmetric real matrix.
Non-negative.
Non-negative. That's all we want to show. Negative geometric mean. What about this? Negative geometric mean? This again has a very similar form. I mean, except for the fact that the Hessian has a minus QQ transpose. There's an n times diag 1 upon blah blah blah. What is Q here? It's of this form. What is Q here? Q is also going to be of similar form. 1 upon x I types, right? So why don't you think about it? This is again this you might be able to prove this using some similar Cauchy-Schwarz derivative. Okay, so with all this, we are now equipped to talk about subgradients. So subgradients help generalize the concept of gradients to non-differentiable convex functions. Why is convexity required? As I said, when you have a convex function, you have a convex epigraph. Okay, convex function implies or is equivalent to convex epigraph, which implies supporting hyperplane, which in turn leads to the notion of subgradient, of which gradient is a special case. This is the trajectory of our reasoning so far. As I said, we always go first with intuition and then possibly some proof. Proof is little laborious, but this is the idea. Now, in this case, right? Is this function convex? One you see on the board, is it convex? Yeah, it's only convex in this region. Like if I were to, so let's say, right, if I were to clip out this region, okay, so if I had to clip out this region, then I probably would have, right? I had to clip out this region. Then it's subgradient overall, but unfortunately that's not the case. So so there's no supporting hyperplane otherwise for the whole entire function. That's the problem. If the function is not convex. In fact, to say that a function is differentiable at x is for a convex function is to say that there's a unique linear tangent which underestimates the function. Of course, modulo convexity. Right? In this case, the function itself is not convex. Okay, so if a function is convex, of course, you have this, right? So if a function is like this, even if it's not differentiable, you're basically saying that there's a gradient everywhere, but at this point, you can do something called the subgradient computation. At this point is a point of non-differentiability. So let's take that as a canonical example. Sorry. Okay, so here, if you consider the normal to both sides, this is a case of piecewise linear function also. You take the normal at, this is what, like the hinge loss, right? Hinge loss, or some of these functions which are step or increasing approximations to step. So here at this point, you can come up with a normal both ways. And now if I identify, maybe in a different color, I identify the so-called supporting hyperplanes also at this point. But there's not just one supporting hyperplane, multiple supporting hyperplanes, right? This is for this epigraph of the function. As I said, the convex function is convex, epigraph is a convex set. So I'm talking about its supporting hyperplanes here. So do you see that you have now come up with a range of support, a set of supporting hyperplanes. Okay, so anything between this and this is supporting, correct? So by identifying this normal, the two normals, basically the two normals have also given me a set. This is what I've showed you. Well, these are supporting hyperplanes, and these correspond to subgradients. Well, subgradient with a negative with a -1, like this, right? This is a space -1, and we'll denote this subgradient or instance of subgradient as nabla-F. Actually, nabla-F is going to be denoting what we call the space of subgradient, the subdifferential. So is this intuition clear? The simple example. Otherwise, what I've shown at the top is what happens when your function is differentiable everywhere. Then you have just a unique supporting hyperplane and a unique gradient or subgradient. Okay, so some questions Okay. So what have we done here specifically? Uh, so we have taken H to be some random vector in the subdifferential. And we know from definition of subdifferential that H transpose y minus x should be less than or equal to Fi minus x. It's exactly the definition on the board. Uh, now we have used the definition of derivative itself, in this case, directional derivative. And then we do some multiplication. Okay, so you take this, multiply both sides by norm of y minus x. So what do we have here? F of y minus x is less than the derivative, the dot product, directional derivative, scaled plus an epsilon, scaled by the distance of y and x. Now here is a trick. After this is all, there's no trick so far. You just used the definition. The trick will be to basically show that since this holds for any epsilon, as I shrink the epsilon, it has to become one element. That is a basic manipulation. Okay, you should know the proof trajectory. Shrink epsilon, because see, that's supposed to hold for any epsilon greater than 0. So how do I do that? So we do some rearrangement, right? So sorry, what have I done here? I've said that given that H is in the subdifferential, you will have this inequality H transpose y minus x is less than or equal to f of y minus f of x, which I know is less than or equal to the gradient transpose, right? That's the definition from the previous slide. So H definition has now been tied with the properties of the definition of directional derivative. Yeah. Which one? Here, huh? So we know for sure that the gradient is also part of the we know the first order property of convexity, and we are given that the function is differentiable. So therefore, the gradient is also a subgradient. I mean, the gradient first order property also holds. So by virtue of that, f of y minus f of phi is greater than or equal to f of x plus blah blah blah. Yeah, by definition of gradient in this case. In this case, yeah. So we know that the gradient is a subgradient. All we are trying to prove is that the gradient is the only subgradient. Okay. Thanks for the question. Okay, so this is clear, right? This gives you an opportunity. This entire thing has given you an opportunity to squeeze things out. Okay, so what are we going to do next? We'll rearrange and then consider some y minus. So this is a construction thing, right? I want to get rid of delta. See, I wanted only epsilon. Given any epsilon greater than 0, the exists is what we had said. Well, we are taking some value of delta. So consider, sorry, some value of y minus x in terms of delta. So what have we taken? Let y minus x be some delta by 2, blah, blah, blah. So which is given the delta, we have now distance between y minus x to be delta by 2. Right? This is what gives us. So consider y is y minus x, which is has norm delta by 2. So then we substitute for that. And when you cancel out the common terms, what do you get finally? You get that h minus gradient of f of x should be less than 0 for any epsilon, should be less than epsilon for any epsilon greater than 0. This is the key. Now, if it has to be less than epsilon for any epsilon, then they have to be the same. So there are two tricks, right? On this slide, one trick was applying both gradient and subgradient properties together. And the second was consider a particular value of y minus x. Is this clear? Okay. So with this, we go to the question: what happens if the function is not differentiable but convex? Right? How how many such functions exist which are not differentiable but convex? So, for example, there is this very interesting class of functions called the Weierstrass function, which are very crazy. I'll actually show that. There's a Wikipedia page for that. Okay, this is a Weierstrass function. So this is a real function. It's everywhere. Differentiable low. So it basically looks like this, right? So this is basically like fractals. So you zoom into it, you'll find the same form recurring. That's a property called self-similarity. And it is a continuous function. It's continuous everywhere, but differentiable not at a single point. Okay. Anyways, that's not the main purpose of my discussion here. The main purpose is to show that, well, can convex functions also be so weird that they are continuous everywhere, differentiable nowhere? So it turns out that that is not the case, fortunately, with convex functions. So while we talk about subgradients as a rescue act, convex functions are a lot well behaved. Okay, so that we should not need subdifferential everywhere. I mean, that is basically the message I'm trying to send. The message is that convex function is differentiable almost everywhere. The set of points where f is not differentiable is a measure 0. Okay. But that doesn't mean we ignore non-differentiability. But point is, we have a solvable, manageable problem at hand. We won't have weird cases like the Weierstrass function. So the global minima could easily be a point of non-differentiability. So we need to consider that. You can also stumble upon these kinds of kings, right, where there is non-differentiability in the middle, right? So we should talk about subgradients. But the problem is not as pronounced as it can be otherwise. Okay. So this gets us to the next description. Okay, I'll erase the right side of the board. And let's try and look at subgradients and convexity a little bit more in detail. I'll erase this part. Okay. So the subdifferential is a closed convex set, which means it actually contains its. What do you mean by closed? You'll consider certain sequences and the sequences will converge. You can think of it as basically it will contain its boundary. Okay. So, so this set is guaranteed to be also non-empty as long as a function is convex. So let's look at some calculus properties. Okay. So first is it is a closed set. The second is that what I just demonstrated here, and then its generalization, the previous slide, the pointwise maximum, you can actually derive the subdifferential of the pointwise maximum of multiple functions, convex functions, by looking at the subdifferentials of those individual functions. Okay. So you remember I talked about this particular space, right? So what is this? This is nothing but the convex hull of the union of all those subdifferentials. Okay, this particular space that I pointed here to, this space. Okay, this is the convex hull So I have defined this to be a. Okay. So this was, we'll take the special case. When the two functions are just linear functions, you know that the subgradients, what will they coincide with? Zero everywhere, right? Um, um, if it were, let's take a slightly non-trivial example. So generalizing these two. Okay, so something like this. I'm trying to make the subdifferential look similar. Okay, so if we had this, then you know that. Oh, sorry, this has gone down. Okay, so the green curve and the pink curve. So you have these two normals to the tangents. And what have I done? I've basically considered the um, the tangents here. If I take all those tangents, right, ranging starting here, um, this was also erased. It's starting here until there. So this is a convex hull that we are referring to. The supporting hyperplanes, right? Or you can think of the normals, the convex hull of the normals also. In fact, that is how we have been trying to denote subgradients. Subgradients were always have been denoted as normals padded with a -1, the function space. So this is the second property. The third property, any questions? We have done this for max now. How do you think this will hold for suprema? Instead of maximum, max of Fi's, if I generalize this to supremum of F, like we do in the case of norms, right? We defined matrix norms, matrix matrix induced vector norms. Also, we had two types of norms: matrix induced vector norms and matrix norms. And both of them use notion of suprema. We had a division by the norm of the vector to keep that bounded. And the max was over all such vectors. How do you think this will pan out to be? By the way, I hope you understand what is active functions here. So I didn't write that on the board. Actually, I should correct this. So this is convex hull over all the indices of those functions whose value at x coincide with the max value. Okay, I mean that's what I meant here. So here, at all points on the green curve, sorry, on the pink curve, here the max coincides with that pink curve. On this side, the max coincides with the green. Green got erased here. Yeah. Yeah, green got erased. So this is with respect to all such active points. So those points have a name, or the active functions. Right? The points corresponding to where the active functions take the max are the active points. So active points / active functions. So you will consider those. Okay, so what happens if you have a supremum? Hmm.
That case, there will be no active.
So you don't expect a non-empty set, or you don't expect a set beyond a singleton set, right, of active functions. There will be active functions at every point, obviously. So active functions are those that coincide with the max value. I mean, it's not that it will never attain the value. It may not. So your point is it may sometimes be empty. That good point. So for supremum, okay, so very good point. Yeah. The set of active functions could be empty. Yeah. So what would you do? Small extension. Could you consider some kind of closure? So what's basically happening is that the boundary is not, I mean, the limit points. So supremum is all about this limit point. The limit point itself has to be in my search space somewhere, right? So if I consider a closure, I'll actually be including the limit points. In fact, one of the properties I said is that the subdifferential is a closed set. The limit points must be in the set itself. So what if I explicitly include the limit points? Then will my problem be solved? Can I go ahead with this similar definition? Right. So it's a good point. Okay, so this is just a depiction of what the active functions are here. Right. What I'm trying to say here to this illustration is, if these the set of active functions is not there explicitly, it may be there as part of your closure. Okay, so or slightly more enlarged here. So yeah, here the points are f1, f2. Here each of these points, the active functions are f1, f1 and f2 respectively. Okay, so if you have general pointwise maximum or supremum, actually I have used maximum here still, but you can, let's take the case of supremum, we'll hold. So there what you'll do is, as this S could be infinite in size. So you will take the union of all those. So question was whether we should take closure inside or closure outside. It suffices to take a closure outside. So it's possible that in terms of the active functions, at some places the active functions don't exist, in the sense that point was never achieved. But that's okay, right? The overall subdifferential should be a closed set. So you take this, do the same thing. Take the same thing. The convex hull of all the union of all the subdifferentials with respect to those active functions, and then take a closure. Okay, so the only difference is so now instead of I, I'll have S. S such that fs equal to x, f at x. Okay, so that's when the situation has changed. Actually, you can do this for supremum, so I'll just put it as supremum. And this is addressing the point I have written below. Is this okay? Okay, so I'll in fact show an interesting result, um, a generalization of the Cauchy-Schwarz inequality. So what do you think will be a generalization of the Cauchy-Schwarz inequality? Yes, take some guess. What will be the generalization? What does Cauchy-Schwarz inequality say? It'll be nice to first write down the form you know, right? Which is the U V transpose U, the absolute value. What do you know about this? Is this less than equal to the product of the Euclidean norms of V and U? You know this? Can I write this differently? Actually, this results from an optimization problem. What is the optimization problem? Okay, by the way, I have not completed the story, right? And equality, if and only if, when is the equality going to hold here? If U is alpha V. For some scalar alpha, right? So can I write this differently as an optimization problem? Max, supremum, whatever you want. So what is the max value of V transpose U? You want to put it that way? Max value of V transpose U is fine. So max of V transpose U subject to something. So in fact, let's assume that one of them has some norm upper bounded by 1, right? So okay, what can I say? Sorry? Less than or equal to this one. And this takes a maximum value equal to U, right? So under a certain bound. Now, can you think of changing the norm? See, as I said, one of the most interesting cases for us with respect to the supremum was with norms, right? It gave us matrix induced vector norms, it gave us vector induced matrix norms, all of that, right? So question, how about generalizing Cauchy-Schwarz to say some P norm? So what if I say this norm on U less than, right? I said some norm on U is less than equal to 1. That is a P norm. Okay. Would that result in some other interesting property? Say when I dealt with U with 2 norm, I get a 2 norm. Okay. So I've not yet given you the leaked out the entire answer. Okay. So I'm just trying to give you some more food for thought as we progress. Okay, so yeah, all these norm we'll need a closure, right? So we'll need to look at closure when moment we start looking at suprema. Okay, so I'll come to that in a few minutes. The Cauchy-Schwarz thing, but let's take a very simple example before we go to the generalization of Cauchy-Schwarz. So let's take one norm of x. What is its subgradient? Very simple. You should try and write down, right? One norm of x. How do I can I use any of these properties? The subdifferential of f is the convex hull over all the active functions of the subdifferentials of those active functions at that point x. So we are differing Cauchy-Schwarz for now. I'll come to that, but I want to take a simple example. Okay. Yes, there's 2x, one norm of x. I want to look at the subdifferential. Yeah. What is the subdifferential of one norm of x? How do I write one norm of x? Is there some creative way of writing one norm of x? Huh? Can I write it as a max? Can I write the one norm of x as a max? Max over, how is it defined by the way? Is the sum of the absolute values of xi's, right? One norm of x is sum of absolute values. What is another way of writing absolute sum of absolute values? It is basically a max over every s, which is a -1 plus 1 vector of S transpose X, right? So it's a max, oh sorry, max. You see this? Max over S in -1 plus 1 vector of size n of S transpose X. So how do I use the convex hull? So the convex hull in the sense, how do I first find the active functions? So I want to look at so this subdifferential of one norm of x is the convex hull of something. What is it the convex hull of? Multiple maxes, right? Each of them, what will they give you? S. S, right? In terms of the active functions, you'll get SIs, right? Okay, so the first step is writing down the, so let that unwind on the slide, right? So, sorry, I've used a V there instead of X. That's okay. So, max of V in 1 minus 1, V transpose X. So, this is basically the max of all those possible combinations, right? So, I've used S again in the board. Pointwise maximum of, so there are 2 raised to n such functions. Okay, I've depicted this on the board. If you take, for example, x to be -5, -6, -7, -10, in case you didn't understand, right? If you take the first configuration, -1, -1, all -1s, that in some sense is going to give you the best combination, right? As against +1, +1, which will not be the best for -5, but for +1, etc. will be good for 5, 6, 7, 10. Or some other combination may be good for when the signs are just exactly flipped. Basically, you need, sorry, signs to be exactly matched. The signs to be exactly matched so that when you multiply, the sign gets flipped. You understand this? So this is what those kings correspond to, right? So what do the kings correspond to here? The kings here. The kings are the places where there are active functions. I mean, there are more than one active function. Sorry. Active functions are everywhere. Right. Here also there's an active function, but there's a single active function. Here there's a single active function. Right. The issue is when you have these kings where there are more than one active functions. What would be the more than one active functions? When would be you have more than one active functions? Sorry? Whenever the component has 0, right? So if I had x to be 5, 6, 0, 7, 6, right? Then in this place of the 0, I don't care whether I put a +1 or -1. Doesn't matter. So active functions will correspond to those places where there are zeros. Okay, so let's uncover that. So how do I write this convex value? What would these active functions correspond to? So wherever there is a non-zero element in X, you know, there's exactly one element I need. Minus, the sign is basically going to be flipped. The sign minus of the sign. Oh, sorry. The sign itself. So that the product has a flipped sign. So, and wherever there's a 0, it will be anything between anything -1 + 1. So convex hull will actually reflect there. Okay. For the places where there is a 0. See, that is, otherwise it's just going to coincide with the function, right? Okay, so I've just written this in more details. So let S star be the set of S such that for each S in S star, the value of X transpose X is the same max value. That is what we mean by active functions, right? This is the definition of active functions. So I've written this in slight details. So here, moment you have X is 0 here, then there are two configurations of S that both give you the same active function. So think of this S as an index. It's a finite number, 2 raised to n, but there are still large number of indices. So in this case, there'll be two S's that contribute to the active function. So S transpose X is 6, S transpose X is 6 in both cases, right? So at a point X, there could be multiple S indices which yield that maximum value. This is S star X. So I have given a more some reason. So how will I plug in S star X here? 1 over S star X of the subdifferential of S transpose X. The function of S transpose X. What is that? Subdifferential of X transpose X is always, sorry, did I? Yeah. Yeah. S star X. Yeah, that's okay. That's okay. So, actually, I should put an S in S star X of all such S star X. Right? So I have got some more ammunition to move forward. Okay, so this is exactly what I wrote. Now so what is the subdifferential of S star X? S star or S transpose X. What is the subdifferential of this? This is simply Now I have simplified, right? S transpose X for a single S. What is the subdifferential of S transpose X? Huh? It is simply S. Okay. So I revealed that on the board by mistake. I wanted to hide that, but nevertheless. So this is nothing but, okay, so I'm going to just erase this. I hope you've written it. This is nothing but S. This is nothing but S. I have simplified my problem, you see, by virtue of that calculus property of subdifferentials. Now, how do I compute this? This should be very simple. What is this? So here S star X corresponds to both the functions. So I will just take the convex hull. That's what I've been doing so far, right? Here also on the board, I've done that exactly. I took the convex hull, and at all other points, it's simply S. So is this clear? So if this is clear, then we go to the more ambitious project which I embarked upon, which is the generalization of the Cauchy-Schwarz inequality. So one norm of, this is clear, one norm of X, its definition, the subdifferential of its one norm.
Boundaries will be only at places where S contains 0.
X contains 0.
Talking about when it is plus 6 and minus 6, and there is plus 1, 1, 1 for in S. Say we have
In X.
we have positives.
So his question, let me clarify here. His question is, what if X had minus 6 here, 0, whatever, and 6. Let's say this was a simple vector. Is that your question? Minus 6, 0, 6. So for 0, I know that I can take multiple values. Can I take multiple values here and here? No. Or even if they were the same sign also, no. Because we are looking at a gradient. See, our function S was max of S transpose X. That's the definition. But the S that maximizes for any given configuration, like minus 6, 0, 6, that's a fixed one S. So all your, so if you look at it this way, right? So this S transpose X, there's only one S transpose at any instance of time, and you're taking max over all of them. Now it turns out that the configuration S for which you are, you are allowed to have multiple values here because of X being 0. Yeah, that is inconsequential. Whereas this is of consequence, but still a gradient is a partial derivative only for that component. Is that clear? Is that clear? Sure. Okay. So if you're done with this, let's look at the more ambitious project for us, the special case, the P norm, right? And I said the P norm has a very interesting connection with the Cauchy-Schwarz inequality and the subdifferential for the P norm. So why are we interested in a generalization of the Cauchy-Schwarz inequality? Because it will give us a subdifferential of the P norm. Okay, so let me, can I erase this part? The one norm use case is a simple use case. In fact, we'll now see how we can, there's another way we can derive the subdifferential of one norm. See, a special case of the P norm is one norm. All we are going to do is generalize this Cauchy-Schwarz inequality and apply our generalization for P equals 1, and we should still be able to derive, right, the same expression. Okay, so I'm going to, with that, I'm going to just erase this part. And that's why I wrote this. Okay. So the special case is when you have the P norm. And since we won't be doing the proof here, only the intuition, unlike the one norm, go a little faster, only to the intuition. Okay, so it turns out that there's an interesting way you can write down the P norm. The P norm is nothing but the max over all possible Zs, okay, whose Q norm is less than or equal to 1 of Z transpose X. Okay, so So you look at this, right? Max over 2 norm of u less than equal to 1 of v transpose u is, sorry, was basically what? Is the 2 norm of v. This is the Cauchy-Schwarz version of 2 norm. So we have something called the Holder's inequality. And Holder's inequality says, well, a way you can define the P norm is you take max. Is this visible in green or no? Okay, you take the same thing, but I'll change the notation to be consistent with the board. So I have replaced the u with a z, the 2 in the u with a q, and the x with a u. So I've this has become x, this has become z, and this 2 has become q. It turns out that under this simple replacement, this is nothing but the p norm of x, where 1 upon p plus 1 upon q equals 1. No, this is not a definition. This is not a definition of P norm. P norm, Q norm we have done before, right? P norm, Q norm is what? For let's say P and Q are natural numbers. Then we know P norm of x is summation over all the absolute values of the indices xi's raised to p, the whole raised to 1 upon p. That's a definition for now. Okay, we'll just stick to that for now. But you can also have the same thing. Right? You can define it otherwise also, even for non-natural numbers. Let's stick to natural numbers for now. Okay. But point is, obviously you'll have to deal with non-natural numbers here, given this constraint. Right? But it's the same definition. We'll use the same definition. Let's consider the case of p's and q's greater than 1. And if you want, I'll write it down here. That this is p q greater than 1. Sorry, greater than actually greater than 0, and we'll take greater than 1, and the p norm of x is summation over I, absolute value of xi raised to phi, the whole raised to 1 upon p. That okay? That's the definition. So what has happened here is under this simple generalization of Cauchy-Schwarz inequality, you're seeing some very interesting relationship. So why do I call it generalization of Cauchy-Schwarz? Do you see that Cauchy-Schwarz is a special case? What's the special case? What is the Q here? A P here? P is also 2, like Q. 1 upon P plus 1 upon Q is still equal to 1. So that's why it's called a generalization, a Holder inequality. Okay. So how does this give me some leverage for the subgradient computation? How will I get the subgradient? So why is this definition? Let's say this the way we got here was I took one norm of P, one norm of X to be max over S transpose X, right? Then I had seen a Cauchy-Schwarz inequality. I suddenly got excited and said, well, any Q norm can be written as a max. Now, can I get the subgradients for the Q norm using this expression? Well, for the P norm, let's say I want to get the subdifferential for P norm of X. I write it in terms of this, the max. Each of them is a Z transpose X. All I have to do is compute the support. You see, I have reduced the problem. You understand? So as an application, let me show this here itself. We don't have so much board space. That's a problem. I have to keep erasing. Um, I'll use a little bit of the board and sorry of the slides and then use the board. Otherwise, right? So your homework is will try and derive the subgradients, right? But I'll just state the Holder's inequality on the next slide, right? So what is the Holder's inequality? I just showed. We have just generalized the Cauchy-Schwarz inequality to P norm of x is max of zq less than q norm of z less than equal to 1 x transpose z. Okay, so the point is, this is our kind of our first exposure to duality. I said duality is also an interesting concept in optimization. So what is happening here is the primal view of the norm, P norm, is like filling up a mold. You had asked this question, isn't this a kind of a recursive definition, right? So primal, if you use the primal, it's not a recursive definition, right? It's just giving you an inequality with respect to a defined P norm, right? So primal says it's like casting up a mold. If you have to create some murti, right? You can fill up a mold to create a murti. So that's the P norm, which I defined. But the dual is, you can also create a murti by chiseling out, right, from a stone. So carving out unwanted material from the base object. So that is exactly what is happening in the Holder's inequality. You see, I'm chiseling away based on Q to define P. Or you can think of, if you remember, I talked about supporting hyperplanes and convex sets. One way of defining convex set is saying, well, it's a convex combination of so many points, right? Like convex hull. Another way is saying, which is the intersection of multiple supporting hyperplanes. In fact, that's very naturally done for polygons. You can define polygon as intersection of multiple half spaces, right? So this is like what is happening here. It's like carving out unwanted material from the base object. Okay, so I think I give you enough perspective. Now, right. So then the question is, you can basically write down. I mean, I've just plugged in the definition. So subdifferential of f, when f is the P norm of x, is basically y, such that the Q norm of y is less than or equal to 1. That's how it should be. And y transpose x, this is basically the support. Y transpose x is the max of z transpose x. This is exactly what we did for S in the case of one norm. So try and plug in one norm. It will become very clear. Okay, so imagine I have plugged P to be 1. Now what is Q? If P is 1, Q is? Q is? Yeah, Q should tend to infinity, right? So Q should tend to infinity. And what do you know about the infinite? I mean, the infinity norm is a max value, right? So just plug it in here. So it is basically saying all those components, all those y's, where the max value of y is less than or equal to 1. Okay, because we were already, so this is a special case where we are allowed only the z to be less than or equal to 1. So this zq was, sorry, what? Zq was what? In this case, the infinity norm, we are basically saying that each element should be -1 or +1. You remember? The zq norm, zq less than or equal to 1, where q tends to infinity, is like saying that each element is -1 or +1. And such that the y transpose x is the max. Basically, it's like saying support. The S, think of this y as a S, right? You're saying S transpose x should coincide to be the max value, S star. Okay, so I hope you must spend a little time dwelling on this. There is no closed form expression. Okay, you may think, oh, let's simplify this. There's no simplification. We'll see simplification of this when we look at sufficient condition for point of minimization. Okay, so just wait for the next class. Next class, we'll show how this gives you some very strong tools to show sufficient condition for minima of non-differentiable convex functions. Okay. So this doesn't get simpler than this. Okay. So this is the homework. Can you derive the subdifferential of one norm of x? Understand this, right? This connection between Holder's inequality and this is okay. Any questions? Okay. So the other homework problem I want to leave for you is we have what did we see in the calculus of convex functions? We saw max, supremum. What else? Linear combinations, affine transformations. Yes. So can you add to this list? We have seen only three properties essentially. This is the calculus of subdifferentials. Can you grow this calculus? Did we also see composition? F of g of x. When is f of g of x convex? Sorry? Yeah, is f is increasing and g is convex, and or if g is concave, f should be convex, of course, in both cases. G is concave and f is non-increasing and convex, or g is convex and non-decreasing and f is convex. We saw these two cases, and then we also saw f applied to multiple g's. What happens to the subdifferentials in those cases? The composition is the other interesting thing, because I like log sum x we show through some composition. Okay, so that's the second homework. Just think about what else you need to make subdifferentials useful in practice. Otherwise, if you don't have calculus, you can't be computing everything from scratch. Okay, so these are two homework problems for you to think. Please do consider that. We'll meet on Tuesday at 9 p.m. I have sent the venue. Is this CC 103, right? Was it 103 or 1? I just don't remember the 101 or 103. Was it 103? So CC 103, you know this building, right? The computer center, the new computer science building, which also houses computer center. That's in the second floor. It's called the second floor, right? I think I forgot. I've lost track of what is first and second floor. Things have been changing in the Crescent building. Yeah, but it's like the first floor. Thanks.